Hi, I'm Shu-Bo. Today I'm gonna present my research, which is recurrent neural network-based joint trans-constraint stochastic multiplier control for DICOTS Conference 2022 in Busan. Here's the outline for the presentation today. First of all, I will give you guys some general concepts of joint trans-constraint stochastic multiplier control, and then I will show you some difficulties in the existing studies for handling SMPC problems. Next, we will move on to the first step of the presenting approach, which is the quantile-based reformulation for the joint trans-constraint. After that, we will move on to the recurrent neural network approximation for the joint trans-constraint SMPC. After that, I will move on to the case study to show you how to use the proposed approach to a real SMPC problem. Finally, I will give you a brief summary at the conclusion part. A SMPC problem is composed of different stochastic optimal control problem (SOCPs) at different time steps. A SOCP can be formulated as this here. This SOCP tries to minimize the expression of the sum of the cost function over all the time steps. And subject to these constraints here, the first equality constraint stating that the system state x at time step z plus 1 is equal to the output of the system dynamic model, which is a function of system state and control input anchor C. And this inequality constraint is saying that it is a joint constraint. And we have the constraint function gi, I is from 1 to p. We want these p constraint functions to be less or equal to 0 simultaneously with the probability greater or equal to 1 minus epsilon. And this equality constraint says that x0 is the initial state, which is equal to the real state measured from the real system at the time step t0. SMPC is composed of the SOCPs at different time steps. Well, let me go through the whole procedure of the SMPC. First of all, we can measure the state of the real system at beginning to get the initial state, and based on the initial state, we can solve the SOCP, and then we can obtain the optimal input sequence, and we can apply the first element of the obtained optimal input sequence to the control system, and measure the state of the control system at the next time step, and use the state at the next time step as the new initial state. And based on this new initial state, we solve the SOCP. And we repeat this procedure again and again over all the time steps. So that's how does SMPC work. SOCP in this study is actually a joint trans-constraint problem. However, there are some difficulties involved for solving a joint trans-constraint problem. Like joint trans-constraint problems are difficult to solve as they require addressing the multidimensional distributions. A joint trans-constraint problem is convex only when the following requirements are satisfied. The first requirement is that the constraints in the joint trans-constraint are generally convex in both distribution variables and random parameters. And the second requirement is that the involved random parameters should follow log-concave distributions. There are some common methods proposed to address SMPC problems like stochastic tube approaches, sample-based approaches, scenario-based methods. Stochastic tube approaches suffer from the issues that they are limited to individual trans constraints and unable to address hard input constraints. Both sample-based and scenario-based methods suffer from similar issues that they both have high computational cost. So our proposed approach is to propose an approach that has relatively low computational cost and also can handle joint trans-constraint problem and also be able to address hard constraints for input or any other control variables. So let's go to the quantile-based reformulation, which is the first step of the presented method. Let's go back to the simple definition of the joint trans-constraint here. And this joint trans-constraint can be reformulated as this form here, which is the probability of g bar less or equal to 0, and this probability can greater or equal to 1 minus g epsilon. And g bar is equal to the maximum of gi, I is from 1 to p. And this formula can be further reformulated as this form here to be the quantum-based inequality here. This quantum-based inequality is saying that the 1-0 quanta of G bar should be less or equal to 0. This inequality is the same as the joint constraint here and here. However, the quantum function here is different from the joint constraint here and here. The reason why we use quantum-based formulation can be answered by using this figure. Well, this figure, the vertical axis is the function value HU, and the horizontal axis is related to the distribution variable or input sequence U. Orange curve represents the 1-0 quanta of G bar. G bar is the maximum between G1 and G2. G1 is related to C1, which follows a standard normal distribution. And G1 is in this form. G2 is related to C2. C2 follow a uniform distribution in the range of -2 to 2, and G2 is in this form. And the blue curve represents 1-0 minus probability of G bar less or equal to 0. We can get this form simply by deriving from original joint constraint. This is the original joint constraint. If we simply move the guy on left-hand side to right-hand side, we can get this function which is represented by the blue curve. As you can see, the orange curve has better convexity than the blue curve. So if I use the model to model the orange curve, that would be much more easier than to model the blue curve. Why we care about using a model to model the curves here? Well, this question will be answered in the following slides. Just bear with me. So after have the quantum-based inequality, if C is high-dimensional random parameter, the quantum value will be very difficult to compute. So we have to use empirical quantum function to approximate the real quantum function. And the empirical quantum function can be expressed as this complicated form here. But a more intuitive way to understand the empirical quantum function is to understand it as the G bar M here. G bar M is the m's smallest component of a set. In this set, there are different G bar values based on different realization of C. Let's say we have n samples here, so we have realization of C1 to the realization of Cn. And m is equal to the m multiplied by 1 minus 0. For example, if m is 95, G bar m is the 95th percentile of this set. Okay. So let's go back to the original joint chain constraint in the SOCP. It is the joint chain constraint in the SOCP for the time step from 1 to k, and it can be further reformulated as the quantum-based inequality based on the empirical quantum by the previous step I just mentioned. And you should know that this quantum-based inequality is for different time steps from 1 to k. And then we further use the recurrent neural network to approximate the empirical quantum function here. And the prediction of such neural network, recurrent neural network, is the Q hat. The reason why we want to use the recurrent neural network to predict the quantum value to approximate the quantum function is because if you directly try to compute the empirical quantum function, you have to run the model system multiple times based on an input sequence just for one quantum value. If you want to solve SOCP with directly computing the quantum function to get quantum values, that will be super time consuming because you have to run the model system multiple times, tons of times. That will take lots of time. So if you use the recurrent neural network to learn the relationship between quantum value and the input sequence, you can just compute the quantum value just at once based on an input sequence. So if you try to solve the SOCP with the recurrent neural network involved, you can save lots of time because you don't have to run the model system model multiple times. And also, you don't even need a system model anymore because you already have the recurrent neural network that can tell you about the relationship between the quantum value and the input sequence. Sometimes system model is very time consuming to compute because system model may be a first principle model that takes lots of time to make prediction. So using recurrent neural network to make the prediction of quantum value can save lots of time. And the recurrent neural network can make predictions for different quantum values at different time steps. Like here, the quantum value at time step 1, quantum value at time step 2, to quantum value at time step k, based on the input at time step 0 to time step k minus 1. And the recurrent neural network model we use is called stack and then LSTM model because we stack the LSTM layer to be 2 to make this model more powerful, have more accurate prediction. And then we have the two before neural networks here to encode initial state to be the hidden and cell state for this LSTM model to make different predictions of quantum values at different time steps and based on different initial state and input sequence. And as I say, we need that an LSTM because in a SMPC, we have to solve the SOCP based on different initial states at different time steps. So we need a reconstructed LSTM model that can take both input sequence and initial state at the same time to make predictions of the quantum values. So after we have the recurrent neural network, we can incorporate the recurrent neural network into the SOCP. And because recurrent neural network is a deterministic model, so everything is deterministic in this SOCP. So the SOCP becomes a deterministic optimization problem that can be deterministic solvable. It can be solved by some common solver just because we use the recurrent neural network to handle the uncertainty and the system model involved in this SOCP. And the ML here denotes the stack and LSTM model I just mentioned. So let's move on to the case study. Let me show you how to use the presenting method to solve a real SMPC problem. So this is a hydrodesulfurization process with the hydrogen feed here and the hydrocarbon feed here. And hydrocarbon will accompany with some solver, and the hydrocarbon solver and hydrogen are all fed into the reaction section. The solver reacts with the hydrogen, and as a result, solver can be removed from the hydrocarbon. More collision hydrocarbon can be collected at the bottom of this separator, and the rest of low boiling components can be recycled back to the reaction section. And the SOCP for this SMPC problem of this process is trying to minimize the cost of the hydrogen usage. And the process model can be described by those 5 equations here with 2 differential equations involved. In the process model, log and x3 are 2 random parameters individually follow different Gaussian distributions. And here is the joint transcon trend require xh2 and x5 to be greater than their own threshold at the same time simultaneously, with the probability greater or equal to 1 minus divisor. And 1 minus divisor here is defined as 0.8. xh2 is the mole fraction of hydrogen in the reaction section. x5 is the hydrogen mole fraction in the stream F5 here. So after solve the SMPC problem of the study process 100 times, we get 100 optimal results. And here are the 100 optimal results for F1, F10, their decision variables, X5 and XH2, which are control variables in the joint chain control. You may notice that there's no figure showing the results of F2. That's because 100 optimal results of F2 are all equal to 0, so we can ignore that and do not show the picture here to save some space for this slide. As you can see, most of the results of X5 and XH2 are above the 0.9 and 0.7 those thresholds. So if we have a more careful calculation to see how much of the X5 and XH2 are above the thresholds? And the answer is that above 80% of X5 and XH2 can above their own thresholds. So in other words, the joint transfer constraint in the SOCP of the startup process can be satisfied by using the presenting approach. Also, we compare the proposed approach with the sampling-based method based on Monte Carlo from literature. As you can see, the average optimal objective value from the proposed method is much less conservative than the average optimal objective value from the sampling-based method in the literature. Also, the solution time of the proposed method is much shorter than the solution time of Monte Carlo sampling-based method from literature. So our proposed approach can achieve better performance and with higher computational efficiency than the sampling-based method in the literature. Finally, let's go to the conclusion part. First of all, a novel approach based on the RNN-based model is proposed for the SMPC problems. The proposed method is computationally efficient because of using the RNN-based signal model. The RNN-based model can simultaneously address both JCC, the joint chain constraint, and control system model. The proposed approach can make the SOCP deterministically solvable, even though SOCP is originally stochastic. According to the results from the case study, the presenting method can reliably handle a nonlinear SMPC problem with much less computational cost than the sample-based approach in the literature. Finally, the drawback of the proposed approach is that the uncertainty distribution should be known in advance, otherwise you cannot use this presenting approach. So that's all for the presentation today. Thanks for your attention. We are grateful for financial subsidies from NSERC in Canada and Imperial Oil.